Okay, I'm pleased to announce or talk about our new systems at CSC, also a bit about what we're doing and also some future directions related to AI and HPC, of course, which are sort of one common theme that we are working together, the AI team and the HP team. So CSC, I don't know how well you know CSC. So CSC is the Finnish supercomputing center. We've been around since the 70s and have been hosting all big supercomputing systems in Finland. So there's only one real supercomputing center in Finland. Of course, the universities have some smaller systems and like typically throughout Europe, but really the sort of centralized resources are only in one place. And at CSC and in Finland, I think we consider that also a strength because that helps us to pool all the resources from a fairly small country into one big thing. And CSC nowadays is actually pretty large. If you look at the number of employees, we're over 350 now. We're growing very rapidly actually at the moment. Our turnover is tens of millions, and we're expanding both in number of employees and also in what we actually do. So we're headquartered in Espoo, close to Helsinki down here, but then also our data center that I will talk about more at the end of this talk is in Kajaani. So Kajaani is here in the middle of Finland, so 600 kilometers north from Helsinki. And the reason there is really that we can have a lot of space here. We have a lot of nice cooling and also a lot of electricity from nearby hydroelectric power sources. And CS is a company owned by the state and also actually the universities nowadays. It used to be fully owned by the state, but now we also have the universities on board, which I think is really nice. So what do we do? So this is an overview. I will not talk in detail about all of these at all, luckily. But we do, of course, HPC computing and software and storage for those systems. We also do various kinds of data-related activities. We have a lot of training. So we have a training facility at CSC, which is almost fully booked throughout the year. We also have a very nice HPC summer school that we run every year in the sort of forest area close by to Espoo. I recommend that. Unfortunately, this year is fully booked, so you have to wait until next year. But I think it's mostly for PhD students, and I think it has been very well received. We also have a lot of solutions for the wider educational sector in Finland, so the schools, normal schools, and also various kinds of university, and then also things related then to data and fair services. And what I should not forget, of course, is that then one big thing here is that CSC is also managing the network, so the network in Finland for the universities and the research sectors of FUNET, which is then connected to Nordunet and Geant. So that is also one good thing for us, is that we can do lots of collaboration, especially then with regards to data center, to ensure that we have a very nice and good connection from our data centers to the universities and the European infrastructures. So on the computing side, we have our old infrastructure that I will talk a bit more about. So some Cray system, Cray XA40, so one of the first Haswell systems in the world. And then we also have a cluster called Taito, which is air-cooled. We are developing also some scientific software like Elmer, which is a finite element model software, open source, used throughout the world. I think it has a few thousand users at least. So if you have a need for this kind of a multi-physics model, I recommend that. This is one vehicle that we also use for some industrial collaboration, for example, for electrodynamic engines and these kind of things. And we have done also collaboration with Intel to optimize that code to really get it to fly on the latest architectures. FUNET I talked about. Then, in addition to the sort of this traditional HPC bare metal, we also have cloud services, basically OpenStack IS services, both ePerto, which is for sensitive data, and also cPerto, which is more for a general kind of compute. Then we also have other things that are always increasing. We have on the research administration side, we can look at we have computing bibliometrics for the universities for funding. And a lot of different kind of statistic things for those for research administration. We also have provide this kind of collaboration platforms, which then includes wikis and ticket, this kind of issue tracking systems, IRA, and so on, and also this training for the researchers. And then on this side, we have a lot of these different fair solutions so both for storing and also sharing data and finding these data sets with metadata on. CSC is also involved in a lot of these European infrastructures. So CSC we have been working in PRAISE since the first PRAISE project. That is where I have been mostly working in these European collaborations. And CSC is also participating in the Tier 1 side in giving resources, so on the DECI side. But also, if you look at then these Tier 0 resources, CSC Finland has been Finnish researchers have been quite successful in getting resources. Also on the EOSC, we are involved in the European Open Science Cloud, Research Data Alliance, and the Elixir one. So Finland is one Elixir node. So Elixir is for different kinds of life science data sets, providing access to data and compute for that and so on. So that is where we have placed a lot of effort. Now, what do we have? So this is our current sort of supercomputer. I'm showing this. And this is sort of the farewell slide, I guess, because this is a system that will be decommissioned now during the summer. So we are now running this at full tilt. I think the queues are several weeks long already because the users really want to get the final use out of this Cray XE40. So it's, as I said, it was one of the first, if not the first Cray system with the Haswell cores, and it has in total 40,000 cores. And it was debuted at something like position 37 in 2014, but now it has fallen off. And the first phase was installed already in 2012. And also this is a system where we have done some experimentation with burst buffers, so we have a few data warp nodes here too. And this we have mostly used them for some special users with special need, so that they don't really crash our Lustre file system. Then and this is air-cooled, of course. And then on the sort of general HPC side, we have a Taito cluster, which has a lot of different kinds of nodes, which have been procured over the years. So it's a real mix of hardware from many vendors, Dell, HP. There was some Bull hardware also at one point of time, and also installed in several phases. These are installed in these modular data centers. So we have two of these large containers by SGI, where we can basically draw in fresh air from the sides and cool down the systems with a very low PUE. And this is also where we have our current GPU resources. And then additionally, something that we have developed since the last big procurement. So this was also installed in 2014 and 12, so that was the last big procurement that we did. And since then, we have, as many other sites, also developed a very large platform of various kinds of cloud resources. So we have ePOTA. This is really this kind of a very specialized cloud for sensitive data. This is especially used then for different kind of medical data. So it's integrated, that provides then enough security so that we can really handle real patient data. It's been growing throughout the years, so now it's already 7,000 cores, and this is this kind of organic growth, so we add more hardware as time goes. And then the other service that we have is cPOTA, which is more of like a general purpose cloud, similar to, in a way, what CSCS has. So it's also quite close to vanilla OpenStack with some additional tweaks on top of that. And then a new thing that we're developing is Rahti. This is now taking in use as a real service. This is this OpenShift Kubernetes kind of container cloud service. And we're still running that on top of these IaaS clouds, but this is something that in the future we probably also do a real native bare metal Kubernetes. I mentioned these FAIR services. So this is something which is, if you look at how we believe that the users should use our system. So it's not only HPC resources and storage for those, but it's also supporting the full sort of life cycle of a research project. So we have, of course, the cluster and the storage, but we also then want to be able for them to store this kind of data that they have produced. We want them to be able to store it in a state that does not change anymore, so that you can publish it. You can add metadata to it, so you can define metadata so that it's easy to find, and then you can use that, for example, in a paper, and we can also give some guarantees for how long that would be available. And then for the kind of data that we really want to keep around for a long time, we also have this long-term storage service where this can also flow. But it's not kind of automatic flow, but only those data that are deemed good enough, and also, of course, has to fulfill the requirements for different kinds of file formats and so on. So this is another thing that we're working on. And CSC, if you look at the HPC side, where I'm mostly being active, is there's a lot of different kinds of users. And this kind of user community has been growing all the time. So this is now looking at what kind of user accounts we have on the system. And there's a lot of biological sciences, by far the largest. And this is partly because of the new customer groups doing various kind of bioinformatics workloads. But also languages and literature. So we have databases for languages, corpuses of different kinds of languages. This is something. Of course, looking then at the actual usage, so now I'm talking about CPU hours, how much we actually use the systems, that is looking a bit different. So there you have more of the traditional physical sciences, biological sciences, so this is more like a GROMAS kind of molecular dynamics simulations. So these are then a different view. And this is a historical graph, so what has CSC done over the years? So we have actually been pretty much an IBM center and a Cray center throughout the years. If you look at the different kinds of systems we have, so this starts at 89. The growth has been steady, basically tracking what has been available on the technological side. And now this was the last upgrade, and now we have something new coming in here, which is just about time, of course, because not that it's getting slower, but there is a need really to improve performance, but also I think a need to improve what kind of services we're going to give to the users. So we have a new. So already in 2015 we started by developing this kind of a science case for getting a new infrastructure, and now we have invested approximately, or we have secured funding for approximately a bit more than 30 million euros for doing this investment. So it's both for developing this kind of data management solutions and also a computing environment. And we also have got some additional funding actually for AI and also for some competence developing. And this competence development is this kind of funding for developing the services around the hardware that we procure. So different kind, for example, I will actually have a slide about that a bit later on. And the other thing that really changes for us at this stage is that earlier we only used to serve the universities. Now we are expanding also the research institutes. For us always a bit of a difficult spot is the industrial sector. We're not really able to serve those with a very large share. So there's some legal issues for that for us. So we can only give sell a fairly small share to the industrial sector in Finland, and that is something that So this was the science case document that we created in 2015, and then used then for building up the vision of what we want to install. And we basically at the end boiled it down to 6 these kind of grand use cases of what kind of science we want to support and what we want to run on it. Essentially, these may not cover all of the things that we want to do, but it's some kind of overview of 6 sort of drivers that we then can use to build up the story about how we do solutions. And one is, of course, large-scale simulations. These are these classical large HPC simulations requiring a large number of nodes or cores and well-scalable hardware. Also, throughput computing, this is a very big thing for us, of course, because a lot of our users are doing these biological systems. So GROMACs running large amount of data, especially nowadays with AI growing up also in our user community. Is a way also for one use case of AI is to be able to produce data for doing some more improved data analytics on that or understanding more about the data. And artificial intelligence was one main driver also here for us. And this was both a challenge, I guess, on the data side, but also then on the compute side, so how to design. So one vision really here was not to develop a completely separate AI system, but to have something that is able to serve both these kind of throughput simulations on accelerated hardware, but then also the AI workflows. And data-intensive computing and also data-intensive computing for sensitive data. This, in our case, is mostly still about the ePert environment, so further developing the ePert environment. And then also data streams. So in practice, what we want to do in the new infrastructure is improving how we can ingest large data sets from various kinds of instruments that are built up in Finland, or ingesting different kinds of genome data sets that are now being transferred to Finland. And one thing, so many of those 6 drivers that we have selected, and if you look at the real workflow that the scientist does, it's of course not only one of them, but it's a mix of various stages. And hence we want to be able then to, with the different kinds of solutions that we have, then be able to support all of those. So especially then one interesting thing for us is the convergence in a way of AI and HPC. So at least in Finland, people are experimenting a lot with AI. I think it's mostly still on this kind of processing data that you have done with simulation kind of thing. So for example, there's one group that did work with dislocations, so running a large number of atomistic simulations of different kinds of dislocation simulations, getting a lot of data and then using that to training like a predicting system that is able then to predict the properties of other systems that you have not yet simulated. Another project where CS is involved is the NOMAD project, the big EU project, where the idea is to run a large number of simulations, quantum mechanical simulations, to see the various physical properties of different kinds of compounds, and based on this data set then be able to create an expert system where you can then predict the properties, physical properties of compounds that you have not yet seen. And another theme that you can see really in the new projects coming in now into the new infrastructure is different kinds of classical sort of AI workloads where you have some kind of measured data and then you want to learn from that. So especially in the field of medical field, we have a lot of different new projects coming in, both from having various like for example, these actual tissue samples and pictures of the tissue samples, of the morphology of the tissue sample. And there are some groups doing work to really use these tissue sample images to be able to predict also what kind of genes this person has, and then be able to do this personalized medicine and help to improve the treatment, or to look at radiological images and actually find different kinds of features. These are these kind of quite interesting things we have coming in. And of course, data is something that we are very interested in. And that is also somewhere, when I present the systems, we have still some stuff coming in that has not been announced yet, so stay tuned. So I think we have a pretty traditional, actually, storage architecture in the new system with some flash layers still to be announced. But the new sort of thing that we have built in the center here is Ceph object storage. So this is something we originally developed for the cloud infrastructure, but now we are bringing this object storage, Ceph-based, really into the full infrastructure as a centralized storage for creating a lot of new services, but then also to form a basis of being this kind of lukewarm project storage / sharing platform for sharing data. So something below Lustre. I have a few slides also about some like real cases that we have been using as some kind of drivers for this thing. One is, for example, like an example of a large-scale simulation. This was actually one of the benchmark codes also. So this is a Vlasov code, a hybrid Vlasov code, simulating the magnetospheres of Earth. And this is interesting in the case that it really is something where you can throw essentially as much compute power on it as you can, because they are still a bit behind from what they would want to do. And this is somewhere where we also have a new PRAISE project coming up, where we will help them to really both take the step in utilizing new architectures and helping to improve the quality of the code, and to also then introduce adaptive mesh refinement into this thing, because they're still running in 5-dimensional space, so 2-dimensional slice with a full distribution function in each space, and then basically need to add the final dimension here, which in principle would mean that it would be 1,000 times larger problem. And this is something that we hope to be able to run at least at a rough scale on our new systems. Another big group in Finland is the group studying various kinds of climate feedbacks and timescales. And the interesting theory is that essentially in this group what they do is they study what kind of feedback mechanisms you have in the climate. And they are running simulations with various kinds of applications, starting from the quantum chemical level up to then this kind of large climate models. And this is also somewhere where you can really see that there's a huge number of data. They also have real data coming in, and so it's in different kinds of sensor data. And this is somewhere where I believe also that these kind of AI deep learning in practice work is something that they may be quite interesting in. You can see that climate modeling and analyzing that data, these large data have been where that has been used. And then also these sensitive data, so basically different kinds of whole genome analysis to really find solutions to cancers, and with real patient data is something that has been done a lot in Finland. And I mean, I'm not too familiar actually with those science fields myself, but then you can really see how quickly we have grown the resources in our sensitive data cloud. And so this is somewhere where we are focusing quite a lot on, partly because we really want to help the researchers not to really work in a properly secure environment with these data sets, so that they are not too tempted to run them on a platform where you should not really run that. And now, these are now the So DL2021 is the code name for our new infrastructure. It's not really a official, like a public name, but this is the sort of brand name that we have, the sort of project name for that procurement. And these are the 3 new services or systems that we are installing. So Puhti, Mahti, and Allas. And essentially what this is basically a cluster, air-cooled cluster, and a liquid-cooled supercomputer. Pretty much both could be called supercomputers. And then we have this object storage in the middle. And the idea really is that this object storage is the central point in this infrastructure. So the central project area where data sets can be stored, where we can store data that you want to share or just dump some data there. And it's designed to be big enough so that it's, we should not run out of space too quickly. And it's also, while it's safe, we can also quite easily increase the size of that. So this is a way to bind together better our cloud services, so the commodity cloud, so this cPerta cloud and the private cloud, ePerta cloud, and then also our Rahti, this OpenShift-based methods. And one reason why we still have 2 systems, somebody may wonder, is that there's actually 2 reasons. One reason is the phased installations. So we didn't want to install everything at once, but we wanted to have a phased installation to be able to better get our users on board and also to avoid a very abrupt sort of break in our services. And the other reason is also that we wanted to reuse in this procurement or in this installation the existing data centers. So this is air-cooled and will be installed, replacing essentially the Taito cluster I mentioned earlier. And then we have Mahti, which is then replacing the air-cooled Cray system. So Puhti is something that we are installing right now. I think the first racks arrived last week, and some racks are still arriving today. So this is now based on the new Intel Cascade Lake architecture that I think more details will come very soon about that thing. And in total, this is close to 30,000 CPU cores with something like 2 petaflops of performance and InfiniBand HDR. So this is, as far as I know, probably the first machine in the world with InfiniBand HDR, production machine. I think there are, of course, different kinds of prototypes. And this is something that we are quite eager to get. So we sort of targeted also the timetable, of course, to get some interesting new technologies here. And then there's also a parallel file system, Lustre, with DDN, 4.9 petabytes. And this is a fairly traditional system, though this is also the latest generation, so the 18K. And these are currently being installed in Kajaani. And I should mention also that there's various kinds of nodes. So with the various kinds of memory configurations, we also have very large memory nodes. We have nodes with even some local disks. Mostly this is diskless, this system. And then we also have the AI partition. So as I mentioned, AI is one focus. So of course, one reason why we like the Cascade Lake is we're quite interesting to see what VNNI can do for the inference workloads we have. So that was one thing that sort of was tempting. But then also we have 80 nodes with Voltas, so for the 132 gig per GPU, and then these are connected with a dual rail HDR 100 non-blocking. So it's has quite nice interconnect bandwidth. So really hope. So the target here really is to both support GPU HPC kind of workloads, accelerated workloads, but then also to really be able to go to the distributed deep learning training workloads. So we have done a lot of testing with Horovod and these kind of solutions on our current system, which is not as well scaling in per se. So get quite sort of promising results. Another thing we have local NVMe memories there, and are planning to use Beyond also on top of those for the deep learning workloads to really get a fast, high IOPS memory layer, and then doing some work to integrate that with Slurm too. Additionally, we some of our AI users. So additionally, of course, we will then support Singularity. Actually, we have been a bit slow to adapt to use Singularity on our current systems. Partly this is because on the old cluster, we are still running a fairly old kernel. And so we haven't really been able to use that well. So, but on the new systems, naturally, as in many places, we will have a support for Singularity containers to really help users to install and use more of these complex deep learning solutions. And that's also, I think, quite important on the data analysis side there. A lot of users running very complex kinds of Python combinations with various kinds of tools. So that is one focus area really also in this competence development to help us to really get better at supporting that. And then some of our also, we had 26 nodes with Pascal GPUs, so quite a nice resource that too. So that will partly move to the cloud infrastructure more, and then also we will use those as more for interactive accelerated computing. So basically visualization and just interactive testing of deep learning. Something that we need to work on is then some kind of higher level support, for example, support to Jupyter notebooks and these kind of things. So that is still something where we don't have a really clear roadmap exactly what we will use there, but that is something that we are quite interested in, of course, in collaborating. And also some of the topics this morning from CSCS is quite interesting. So for example, this idea of getting like an on-demand resource is perhaps something that I think that a lot of our AI users would like, because the AI users and HPC users have a slightly different mindset often of what kind of access they want. The AI user wants to be able to have immediate access and run quickly, and they're not really interested in this kind of a batch scheduling workflow. I should mention too that actually this, when I say 30,000 cores, it's not really true, because we also did a turnkey solution for FMI, so the Finnish Meteorological Institute. So actually the size of the system is 40,000 cores. So 10,000 of those are then fully owned and used by the research side at the Finnish Meteorological Institute. So we basically did the procurement, installation, acceptance, and operating the whole system. So in total, when you compute that and the other one, it's about 1,000 nodes, the full system. So quite a nice system for us. And looking at the performance also, the step up from our old system to the new system is quite significant. So if the overall number of petaflops is more than 5 here, so that's quite a step up from the 1.7 even in the SISU Cray XC40. If you wonder what the name, Puhti, so this is in Finnish, and that means basically like vigor, or like somehow that you are stamina, you are quick on your feet. Mahti, this is then the upcoming supercomputer. This is being installed later this year, early next year. This is a different architecture than the first one. So we'll actually have quite a nice opportunity to test different kind of CPU architectures, because the first system is the Cascade Lake one, but the second one is Epic Rome based. It's about 200,000 cores in total. And this is especially designed then for, of course, these kind of large scale simulations, but I think it has also, it's similar in other ways, of course, to the other system in that it's also HDR100 interconnect. So I think we will slightly also mix and match the different kinds of workloads. So workloads benefiting from vectorization or benefiting from high thread count may be useful to run on different kinds of hardware. And since all of these are by Atos, so we'll be running also the same operating system, the same environment, and on both of these systems. Finally, Allas. So Allas is our new Ceph-based cluster, storage cluster. So this is a real object storage. We will not use Ceph FS here, but we will use the Rados gateway to access objects, and we will provide an S3 and Swift API for that. And this is quite interesting because this essentially is fully based on open source Ceph, and we have, for this one we are just buying the hardware, we're doing all the installation and all the operating and everything ourselves. And this really is also for us sort of development project partly. So we will be building services and data migration tools. So over the years to really increase the use of this thing. But some of the use cases here really is a project storage, sharing data to the outside, to the internet with good performance. Also ingesting data streams. So it's all about having a modern object storage system where that you can increase over the years, where the lifetime of the file system is longer than the actual hardware underneath it. And also having then gateways or these kind of data mover nodes, enabling you to build this services where you can move data quickly and efficiently without using login nodes or anything like that. And also being able to create use case, support use cases where you both use cloud resources for creating, for example, some kind of virtual observatory, and then also using then the compute traces of the clusters through some API to really enable use cases where you can use both of them at the same time. This is a topic where we are, of course, interested in collaboration. And as I mentioned, competence development, we did this time some investment also in actually, on top of the development work we do in any case, also improve, so some additional investment into really getting the most out of this. So user support and training. We are renewing a lot of training material and the user guides and how we do the user guides. Then also data management. We have improving the support for remote desktop. We're developing, traditionally ePOTA environment has been a very traditional cloud where you just get an SSH connection there through your virtual LAN. But we now also support this remote desktop, so you can. So it's much easier still for the user of this to use it, for the users to use it. Data transfers and also container technologies, microservices, Mahti in practice, and then also investigating these massive machine learning workflows. Now my final slides. I'm not sure how am I time. So this is some new things that we're doing. So as many of you know, or some of you know, CSC-IT is leading a consortium participating in the EuroHPC joint undertaking. So the HPC joint undertaking has a call out currently for hosting these new pre-exascale systems. And the call is closing quite soon, actually this week. So, and the idea there from the JU is that they want to build in 2020 pre-exascale supercomputers that and then follow those with exascale computers 2 years later. And there's a total budget of 300 million for these first generation pre-exascale systems. I think it's about twice the amount of money for the exascale systems. And 250 of those millions of these goes to 2 or more precursor exascale systems. The idea is that the JU provides half of the funding, and then the countries or the consortia that then applies for the hosting then supplies the other half of the funding. And we are now leading a consortium for hosting one of these systems in Kajaani. And why Kajaani? So we are quite proud of the current data center. So I mentioned that we have this air-cooled system with a very low PUE, so 1.03 because of the cold climate up here. But then we also, the new Atlas system with warm water cooling will also have a very low PUE, close to 1.05 or something like that, because essentially we don't need any chillers in that climate for that kind of system. It's at maximum it's 30 degrees outside, and that would be almost a once in a lifetime kind of event. It's also, we have that's very cheap electricity here, and it's also environmentally friendly because it's also hydroelectric. This whole thing is in an old paper mill. So these our current systems are in the warehouse where they used to store paper. And the new systems that we propose in EuroHPC would be hosted then in the actual main hall where the paper machine has been. So this is a picture. So it's a very large location. And because a paper mill uses a lot of electricity, that's why they had their own hydroelectric power. And in general, there's a lot of electricity in the region. The paper mill used more than 200 megawatts when it was running. And of course, also now there's another project on the FUNET side where they are upgrading the whole network in Finland. So this is actually a picture of how it will look in 2020. So there will be 4 independent lines coming in here and a lot of independent lines going to Sweden and the Nordics and also then to Europe. So there's a very good connectivity also to the site. And this is the consortium. So essentially we have all the Nordics, Poland, Czechs, Belgium, and also the Swiss are in this consortium. And I think the big strength here is both that we have a very good set of competencies. And I think we are very happy to have CSCS also here because, of course, with your experience in with BitsDynth and all the work that you have done on especially these kind of new services on a real supercomputing platform, I think this is a really large strength for this consortium. And the other strength, of course, we believe is the hosting location, because it's a very cost-efficient place to host a supercomputer, both in terms of price of electricity and also in terms of other costs. And it also is environmentally very friendly. It's fully hydroelectric, and also with the new system we could actually reuse the heat because in Kajaani they need to heat the houses essentially only 2 or 3 months in the summer. They don't need to heat the houses a lot, but the rest of the year we can heat through the central district heating. We can heat the whole of Kajaani with the power of this proposed system. So that and that's actually even quite a nice business case in terms of selling waste heat from the system. And this is the current status of our proposal. So this was 1 hour ago. So now I hope we will not find any mistakes in it. That was it. Thank you.